Okay, so we're going to pick up where we left off yesterday and try to finish the derivation of kind of the basic principles of self-force. So we had ended with a statement that the background metric for small r scales like r to the 0. First order perturbation scales like 1 over r. Second order perturbation like 1 over r squared, and so forth. So it's 1 over r to the n. And this would come from matched asymptotic expansions. So it has to be a well-behaved expansion that kind of zooms in on the small object, where the small object is the background metric, where space-time is the background metric, plus corrections coming from the interaction with the environment. And then we had our ordinary expansion that was this g, h1, h2, etc. And by insisting that these two things agree, when re-expanded, so they both end up in the form of a small r expansion and a small epsilon expansion, then you find this constraint. And if you go through the matching in a little bit more detail, you find the sum of all of these terms has to give you the metric of the object itself, space-time of the object, as if it weren't interacting with anything around it, as if it were just isolated in the universe. So this is the large R expansion of the object's metric. So say it's a Schwarzschild black hole. This will just be the flat space-time part. This will be the m over r part, m squared over r squared part, etc. And so what this tells us more generally, you can also do a little bit of work to prove that this has to be a stationary metric, which means then that all of the coefficients of 1 over r to the n can be written in terms of the multipole moments of the small object. So the mass appears here, the spin appears here, and the mass dipole moment, depending on your choice of coordinates, quadrupole at next order, octupole, etc. So this entire expansion is then just fully determined by the multipole moments. The subleading terms are not. Some of them are determined via the Einstein equations, but you also introduce new free things at higher orders. So linear in R, actually the acceleration of the object will appear here at r to the 0. Again, actually the acceleration appearing there. And you'll have more and more information appearing as you go to higher order in R. But the leading term is just uniquely determined by the multipole moments of the small object. And that's kind of how information is transferred from this expansion zoomed in on the small object, how it's translated from there into the expansion we actually want to use externally throughout the whole external universe to get our solution, to get our gravitational waves, etc. Okay, so if we go through this in detail, we take an expansion like this and we solve it order by order in R and in epsilon in a little neighborhood around the small object, what we find is that the nth order metric perturbation for all n, no matter how high order you go, has a pretty clean split into two pieces. One is the self field of the small body. So that's kind of the bound field, like a Coulomb type field, that's just moving along with the object. Then we have what's called the regular field, which is a vacuum solution even at r equals 0. So here we're working outside of the small object, but if you then just say, okay, no, I'm going to take my solution and just apply it at r equals 0, this will be a vacuum solution even there, and it's nice and smooth. So this is a smooth vacuum perturbation. And if you're just solving order by order in R and epsilon locally near the small object, this is actually where all the freedom appears, other than the multipole moments. So you have freedom to choose the multipole moments, but then this is also where all the rest of the freedom comes. And this is only determined once you impose some boundary conditions far away. Like say retarded boundary conditions in the real physical big space-time. spacetime of the big black hole. So this is undetermined, it's entirely undetermined from a local analysis, except that it's a smooth vacuum perturbation. And this encodes all the multipole moments. And is singular at r equals 0. So again, in this analysis, we're solving the Einstein equations outside of the object, but if you then just take your solution and just apply it at r equals 0, this term blows up there. So it encodes this 1 over r squared, it encodes all the singular terms. It also encodes things that are higher order in r, but in particular, it encodes all the singular terms. So, if we then write this down in a bit more detail, let me grab another board here. If we write down the structure in more detail, let me just put still just a tilde. This is like m over r plus, as I mentioned, the next term is the self-force, or whatever the acceleration of the object is. So that's F alpha, this is self-force per unit mass, times r to 0. Don't worry about the indices, this is just schematic. Then HS2 has things like m squared over r squared, plus things like m times HR1 over r, and also things like m times the acceleration over r. And actually still back at 1 over r squared order, we have the spin of the object, 1 over r squared, and so on to higher order in small r. So here you see the first dipole term appearing, you'll have quadrupole at third order, etc. So as you go to higher and higher order in the external perturbation theory, you see more and more structure of your small object, and you get more and more singularity, and you get more and more nonlinearity, obviously. Now, in addition, so all of this is just coming from the Einstein equations combined with the matching conditions that we're matching to this small body zone expansion. Another thing that comes just from the Einstein equations with no additional work is actually an equation of motion. Equation of motion for the curve that's at r equals 0. Let's call it Z alpha. So if your small object is a black hole, this isn't a meaningful place in the manifold where the black hole naturally lives, but it is a meaningful place in the manifold of the external universe. Just like when numerical relativity simulates the evolution of a space-time, they still have a point that they can call the position of the black hole, even though they're not getting the metric there and it's not a physical place. It's still in the manifold for them, just like us. But this is kind of an emergent thing that comes from zooming out. When you zoom out, you get this structure, then you can identify where things are singular. That's defining for us a representative curve for the small body, regardless of whether it's a material body or a black hole. Now here, I could have included a mass dipole moment, but I've set that to 0 such that r equals 0 is now the center of mass of the small object, in that particular sense, that there's no mass dipole moment. So the equation of motion you get, I'll first write it down for a non-spinning body. Tau here is proper time in the external background spacetime, g with no hat on it. And d tau, capital D tau, is a derivative, covariant derivative with respect to the background metric, the external background metric, along the trajectory. So let me just define that. So U alpha here is dz alpha d tau. And the equation of motion looks like this, minus a half. So I write it down through second order, which is the highest order that it's known. So here I'm going to write down an HR with no number 1, number 2, etc. This is the sum of HR1 plus HR2. Hopefully I fit it on this line. I should remember this by heart after all these years. Mu. Okay, so this is the equation of motion for the particles. Well, I will be thinking of it as a particle. For the particle's trajectory, as defined in the external spacetime. So it only involves the regular field. It doesn't involve anything from the singular field. I could have made a crazy split of the physical field H into some different HS and HR, and then I could have introduced like just explicit appearances of the mass that would then cancel things in my poorly defined HR. But the natural thing that comes out of matched expansions gives you this form. And let me restate that. And this is up to order epsilon cubed, so plus a residual order epsilon cubed. So this is totally equivalent to a different equation of motion, where I'm going to put tildes on top of everything. So this, I'm missing a square there. This is just the geodesic equation. And it's identical to this if I define an effective metric, G alpha beta. It's the external background plus this regular field. So here again, HR alpha beta with no indices. It's just the sum of all the HRNs. Epsilon to n, HRN, alpha beta. And this effective metric is a vacuum smooth metric at r equals 0. So what we have is geodesic motion in an effective spacetime. So this is called a generalized equivalence principle. So remember in the first lecture, I reminded you that the equivalence principle says every object, no matter what its internal composition is, always moves on a geodesic of the external spacetime if the object is sufficiently small and light. This result is saying, okay, once you account for the field produced by the body itself, it's no longer moving on a geodesic of the external spacetime, but it is moving still on a geodesic of some kind of effective external spacetime. So this spacetime is what the body feels to be producing tidal fields. It's what the body feels it's in free fall relative to. And it is roughly physical in this sense. But if you try to extend it far away from the world line, it's doesn't satisfy causality conditions, so it's not strongly physical, it's just effective. Okay, and I'm going to, so this you can use to derive things, like once you've shown that you can rearrange this into this form, you can use this to derive lots of nice things, but in practice, this is the one you're going to work with, because we're trying to solve field equations in the background, not in some effective metric, because you don't actually know what this is until you solve the field equations. Okay, so I'm going to rewrite this longer one as d squared z alpha d tau squared is epsilon f1 alpha plus epsilon squared f2 alpha plus order epsilon cubed. So f1 here comes from hr1, f2 comes from hr2, but also from quadratic products of hr1 with itself. And so this is the first order self force, this is the second order self force. Yeah. We're solving for the background.
So, anyway, our interest is in observations that fusion are infinite. So, he will always be interested in this equation. So, what is the motivation to that effective equation?
Because this is what the body feels. If you're just out there in the universe, you see this as the external metric. You are in free fall with respect to this. You measure your local tidal field with respect to this. That's the intuition. If you're very, very far away, HR is totally irrelevant. You care about G with no tilde on it, and you care about H, not HR. Okay. Now, this was for a non-spinning body. If I add spin, then what we get is, I'm going to write it in the more compact form up to there. D tilde squared z alpha d tau tilde squared equal to 1 over 2 m r tilde alpha beta mu mu u tilde beta s mu mu plus order epsilon cubed. So this is the Riemann tensor of that effective metric evaluated at r equals 0. This is dz alpha d tau tilde, where tau tilde is defined as proper time in the effective metric. And this is the spin tensor of the object. This equation hasn't been derived to the same level of rigor as this equation. What has been derived is just the kind of leading order term here, so with no r tilde, no u tilde. But there are a bunch of arguments to tell you that this is still almost certainly correct. And what you can see from the scaling, so S, the spin, for a compact object, scales with mass squared. Right, spin is basically mass times angular momentum, or angular rotation. Angular rotation is proportional to the size of the object. So if the size of your object is proportional to the mass, your spin is mass squared. So just like a Kerr metric, its spin angular momentum is little a times its mass, which is scaling with a mass squared. So this tells you you've got mass squared, and then you divide by mass. So this force here is linear in the mass, just like the first order self force. So the spin force, this is known as the Papa-Petru-Dixon spin force, or Matheson-Papa-Petru-Dixon spin force. This has been known actually since the 1930s, without the tildes, so for like a test particle. This comes in at the same order as first order self force. But for orbits in Kerr, leading order, this doesn't create any dissipation. It's like a conservative effect. And so that's, remember, if you think back to the first lecture, if you have a first order force that's conservative, it comes in at sub-leading order in the long-term evolution of the binary. So the spin force comes in at first order, but it still has a subleading effect relative to the first order dissipative cell force. Okay, so here I have been treating the object as extended. I've been solving equations outside the small object. I've then identified, some r equals 0 to represent the object's kind of mean motion, its average motion. But I haven't yet talked about it as a point particle. Well, I've let it slip, called it a point particle, but I haven't shown you that it makes sense to think of it as a point particle. But we can ask ourselves, can we represent the field outside the object as if it were sourced just by a point particle at r equals 0? And the answer is yes, at least at low orders in epsilon, in the small mass. Okay, so the rough way we show that, so we take our local solution, hn alpha beta, is something over r to the n. You do need to know what this something is, but you find it just by solving the Einstein equations, r to the n minus 1 plus blah, blah, blah. And now, like I've been saying, once we have this analytical form, we can say, okay, now let's just let it apply all the way down to r equals 0. So let's extend this to all r bigger than 0. Obviously, can't really extend it to r equals 0 because it's not defined there. Then we can define, and we're really going to take this as a definition, a stress energy tensor. We put a hat on it, T alpha beta. Let me keep index down. We'll define this as 1 over 8 pi times the Einstein curvature. So we've got G1 alpha beta H1 plus epsilon squared G1 H2 plus epsilon squared G2 alpha beta H1 H1 plus order epsilon cubed. So I'm just going to calculate the curvature from these perturbations. I'm going to treat this as a distribution. So when I have derivatives, I'm treating them as distributional derivatives. Everything's a distribution here, which means the way I'm actually defining this is I integrate this against a test function. That's how a distribution works. I integrate this against a test function. I see what I get as my result. And that defines for me what t hat is. So normally you would put in a stress energy tensor, get out a metric. Here I'm putting in the metric. I'm saying Einstein equations, I insist that it holds even distributionally. And then I see what the t hat is that comes out. Doing that at first order is actually very, very simple, but I won't go through the derivation. At second order, it's actually quite tricky because, well, two things. One thing is we already have a theorem from the 1980s telling us that point particles are simply not well defined as sources for the Einstein equation. So if you do PN theory or various things, you might think, what are you talking about? You use point particles all the time. But you use point particles and then adopt some regularization prescription. So normally, if you're just looking at the classical Einstein equations with no regularization, it's proved that generically you cannot have a point particle source. But what's being shown here is that perturbatively, at least up to some order, you can define a point particle source. But it is a perturbative thing. And the reason it gets tricky, so if you're doing linear perturbation theory, distributions are great for linear perturbation theory. That's how distributions work. They're defined as linear things. So everything works nicely there. Here, things get much worse because this thing is so singular that it doesn't have a unique definition as a distribution. If I just plop in these expansions, what I get out is just, it's a well-defined function for all r bigger than 0, but it's not uniquely defined as a distribution on a domain that includes r equals 0. So you need to do actually quite a lot of work to come up with a good definition of this. But ultimately, we are guided by the idea that no matter what we do, we want to make sure that when we solve the Einstein equations with this stress energy tensor, we get out exactly what we put in this. We get out the result of matched asymptotic expansions. So matched asymptotic expansions are our guiding principle here. They are telling us what the correct answer is, and then we just want to make sure we reproduce it. So we give this what we call a canonical distributional definition, which is just a definition that gives us a nice t-hat and gives us the correct solution to the Einstein equations, if we take t-hat as our source. Okay, so if you do that, what happens? Well, you go through quite a long technical distributional derivation, and you end up with a very nice simple result, which is down u tilde alpha, u tilde beta times a delta function, x minus z. So a delta function supported at the particle's position, square root minus g tilde d tau tilde. So this is an integral along the trajectory r equals 0. This is exactly a point particle distribution, a point mass distribution, but everything here is defined in the effective metric. So not only is the object moving on a geodesic in the effective metric, it really looks like a point particle in the effective metric as well. Okay, any questions about any of this? So these are kind of the basic results of self-force theory from local analysis. You never want to match at a boundary. Then you're going to introduce the scale of the boundary. No, we're matching functionally the way I described it yesterday. So we take two different expansions, one in the body zone, one far away. We then re-expand them, and then we match functionally. The coefficients in the double expansion need to match every single coefficient. But this derivation uses very, very little information about the body zone. All I'm using is the multipole moments to find the internal background metric, so the body's background metric. And I'm just using the structure that was imposed by matching, which was this structure. At this stage, that's all I'm using. Once you have a quadrupole moment, which will enter the third order, then you need to know much more about the body zone solution, because the quadrupole moment is not freely specified. The quadrupole moment is coming from the internal dynamics of the matter or whatever is forming that object. And so then to get that time evolution of the quadrupole moment, you'd have to do a much harder matching calculation, a much harder calculation in the body zone to get the actual time evolution of the quadrupole moment. Then once you have that, it would just plop in over here in H3, and all our work is already done. So the real calculation here is solving the Einstein equations locally. The matching is just giving us some structure, and it's defining multipole moments. So to all r greater than 0. So initially, this is only defined in some region reasonably far away from the body. And now I'm saying, no, now I've got this analytical form. What happens if I just say it's for all r equals r, all r except r equals 0? Yeah. So I'm doing an analytical extension of the solution. Yeah.
What is happening in the geodesic in the combined metric?
It-
right?
Yeah.
So in that case, the equation should be exactly zero. Why is it zero up to order of epsilon square?
We've only proved that it applies up to that order.
Okay, so if R is the effective metric up to order of epsilon square.
This calculation, this result, is coming from solving the Einstein equations, and I've only done it to that order. I'm getting that from this. Yeah, I'm just rearranging this equation to get that equation. Yeah.
Also, can you quantify the compactness of the
Yeah, so the compactness is really the statement that the multipole moments, M, L, and SL, scale as M to the L and M to the L. Yeah. So it's just a statement about the scaling. So, if we're thinking of a family of solutions, we want the body's size to scale with its mass and shrink down as the mass shrinks down. Now, it's a different question of how accurate the result is for a given body. So if you try to apply this to a white dwarf or something, its quadrupole moment is going to have a bigger impact than the second order self force. But for a neutron star, this should be a consistent thing to do. And yeah, but for physical bodies, like I said, this is true of if I drop a little black hole here, this whole derivation is true. If I pick up a random object, this is a terrible approximation because all its higher multipole moments are way more important than the self force. Because random objects around us are so not compact that this whole derivation doesn't work. Anyhow, the underlying thing that forces this to be true for us is that we assumed we had that nice expansion where the coefficients were functions of R over M. So that kind of assumes something about the behavior of the space-time near the object that assumes that this is true.
This is a small parameter.
This R over M?
This is a small parameter.
So in the body zone, we were treating this as of order 1. In the far zone, we're treating this actually as huge. This has got a 1 over M in it. Okay. So now I'm going to describe what we do with our results in practice. So one basic idea is called a puncture scheme. And I should actually say, we've never done a second order calculation using that t-hat. Because in fact, in self force, you never actually need the t-hat. As long as you know the local metric perturbation, as long as you know this, that's all you need actually. You don't need to know the stress energy tensor. So the stress energy tensor is just kind of guiding you to how to interpret things. Okay, so puncture scheme. First off, I'm going to say let's specialize to the Lorentz gauge for this description. And in fact, all these results, all the second order ones, and the structure of the first order, that's all derived within the Lorentz gauge. I'm solving the Einstein equations in the Lorentz gauge in the body zone, or at least in some zone near the body. So I'm going to impose this, and then define the linearized Einstein operator, specifically in the Lorentz gauge, which is the box H alpha beta plus 2r alpha mu beta nu h mu mu. So remember, in the linearized Einstein tensor, we had a minus a half multiplying all this, and we had another term that was a derivative of this, which we've now thrown away. So I'm then going to split up my equations into first order and second order ones. H bar 1 is minus 16 pi t 1 alpha beta. So if you've ever done black hole perturbation theory with a point particle, calculating Tucholsky fluxes or whatever, this is basically your starting point. So this is now a point particle in the background metric, not the effective metric. That's what T1 is. And then we've got a second order equation. H bar 2 is minus 16 pi T2 alpha beta plus the quadratic term, which because of the missing minus a half here is now plus 2 G2 alpha beta H1 H1. Okay, so this is very subtle, but the reason I had to impose a gauge condition was so that I could write down a first order equation and a second order equation where the point particle's position is not a background geodesic. Its trajectory in this T1 is not the background geodesic. It's the actual accelerated world line satisfying this equation. So if I were to write down the full linearized Einstein equation with a G1 here rather than an E, then the Bianchi identity would actually tell me that if this is a point particle stress energy tensor, the trajectory of the point particle would have to be a geodesic of the background metric. And I don't want that. If I imposed that, I would massively screw things up. Because the motion of the little object, say it's a big mass, and say we tried to approximate things as a circular orbit. Say it was a circular geodesic. Well, then the real physical motion is not doing that. It's doing this. And you can't capture that with a small perturbation. So we don't want to do this. This is no good. We don't want a reference geodesic. We want the actual inspiraling trajectory to be here. So once you gauge fix your equations, then that's fine. Then I can put any trajectory here. But I'm going to impose this trajectory. And once I've done that, then if I keep going to higher and higher orders, I'm guaranteeing that I'm solving the original full Einstein equation. So this is just a way of splitting it up into a first order piece and a second order piece with a non-geodesic source. Okay, now, yeah, again, these are coupled to this. So this is now a coupled system, yeah. Sorry, yeah.
Describe the motion of fixed objects, and then we also think about the radial inward motion. So we can split the two into this fashion and then simplify it.
Well, if you try to do this, this is a huge correction. This stuff here will then be growing quadratically with time, actually. your second order solution will be growing quadratically with time, the whole approximation breaks. So you just can't do that.
Because the scale is too sharp. The inspiral is happening too fast.
No. The inspiral is happening very slowly. But once you wait a time of order 1 over epsilon, that slow inspiral has accumulated to a massive change. So we're not going to actually use those equations when we solve things numerically. Although actually, basically, that's what we're doing in my project with Nico. But these are just going to be the formal starting point. The way we're going to solve everything numerically is with a multi-scale expansion. But once you're beyond linear order, you can't really think anymore of having sequences of geodesic sources. So, but I'll get to that tomorrow with the multi-scale expansion. So yeah, so this is just a way to formulate the equations so that they are accurate on long time scales, and they allow me to get an H1 that's sourced by an inspiraling trajectory. Okay. Now, this T2 involves HR itself, involves HR1, because my T hat here involves G tilde. But more importantly, the force up there involves HR1. It actually only involves HR1. So it's not good enough to get H1 and H2. We also need HR1 and HR2. So we need a way of getting the full physical H and the regular field. So we need H n alpha beta and HR n alpha beta. The way we're going to do that is we define a puncture field, HP n, that is equal to the singular field I've got there, this local expansion, just truncated at some order. So I already know these local expansions from when I did the matched expansion calculation. I've already got these at hand. I just take them up to whatever order I've got, and then I just stop there, I truncate, and that defines the puncture field. So we define this as Hsn truncated at some order in R. So let's say R, at least R squared or higher. Then this guarantees that HP n alpha beta is equal to the singular field plus something of order R squared. And here R is still distance from the world line. Soon R will become distance from the big black hole, with two different, totally different coordinates. And then this guarantees that if I define H residual, the residual field, as the physical field minus the puncture, this is going to be equal to the regular field plus things of order R squared or higher. So by guaranteeing that I'm approximating the singular field at least to order R squared, then the residual field is approximating the regular field to that same order. And what that means is the residual field evaluated at the particle is exactly equal to the regular field there. So if I need the regular field at the particle, I can just get it from the residual field. And its first derivative is also exactly equal. The first derivative of H residual is exactly equal to the first derivative of HR if you evaluate at the world line. that's because even if I take one derivative, this just becomes linear in R, so it vanishes at R equals 0. So that means if I want to calculate the force, I can just use the residual field. So what I'm going to do is work with the residual field as my numerical variable. So let's go to the physical spacetime. Here, time is running up. So this is the spacetime of a binary, although this method works generically. So say this is my big black hole. This is the world tube of the big black hole. Then somewhere out here, I have my particle moving on the trajectory z. I'm then going to carve out a region around the particle. Inside that region, I want to solve for the residual field. And because this is coupled, in this formulation you have to be solving for h residual 1 and h residual 2 simultaneously, because they're coupled through the acceleration. So we solve for hr1 and hr2 inside this region near the particle. And I'm drawing this intentionally as a big region. This is not supposed to be some tiny little body zone. Then out here, and over here, solve for the physical field, Hn. Then at the boundary, we impose the jump condition that Hn alpha beta is equal to H residual alpha beta plus the puncture. And the first derivative matches also at the boundary. So we formulate a field equation for the residual field in here, a field equation for the retarded physical field out here, and then we have this junction condition at the boundary. So to get the equation for the residual field, all I'm going to do is take these equations and simply move the puncture to the right-hand side. So I just take that h is residual plus puncture, and I just move the puncture over here. So I have E alpha beta, h residual 1 alpha beta equal to minus 16 pi t1 alpha beta minus E alpha beta acting on the puncture. The singularity here cancels the delta function here, and so what you end up with is regular source, sufficiently regular source. And the same idea at second order, the singularities in the puncture cancel the singularities on the right-hand side, and most importantly, they're canceling the extreme, horribly singular things in this G2 term. Canceling that off and leaving us something sufficiently regular that we can just integrate our equation for HR2 and get the second order residual field. And then out here, no, not there, there, we just have the vacuum equation at first order. So we're solving a homogeneous equation outside this world tube. We're solving a sourced equation inside the world tube. And so then at the end of the day, we get the retarded field where we want it. So we get the waveforms, for example, from the retarded solution outside, and we get the residual field, and therefore the regular field inside the world tube. So we get everything we need. Then if for some reason, actually I shouldn't say for some reason, inside the world tube, we're also getting the full retarded field because we can just add the puncture to our solution to this equation. And we actually do need the full retarded field inside the world tube because over here, this is the retarded first order field. This is not the regular first order field. So when we're constructing the second order source, we need to know the full first order field everywhere, not just far away. Okay, any questions about this method? So as I mentioned, this approach is the only approach that's been used as second order, because well, first off, it was only a couple of years ago that my student and I figured out how to ever deal with this on its own, this terribly singular source. So we didn't have even an opportunity to try to solve this equation directly until fairly recently. But also, this is just really nasty to deal with, so you want to cancel as much of it off as you can to have something fairly regular to integrate over as a source. But at first order, this is actually much less common a method. At first order, typically people do not solve a punctured equation or solve an effective source equation to get a residual field. Typically, what people do is get the retarded field and then subtract the singular field to get the regular field and then to get self-force. So that approach is called mode sum regularization. And this has been the main approach at first order. So here the idea is we solve for modes, say H alpha beta 1 L M. So for example, using the tensor harmonic mode decomposition that I described day before yesterday maybe. We solve for the retarded fields mode by mode, and even more frequently this would be Lm omega in a Fourier decomposition. Then, if we want the regular field on the particle, we take a limit from off the particle. So say x goes to z. This is on the particle's trajectory z. Take a limit of the physical field minus the puncture. We then write this as a sum over modes. Lm beta minus Hp1 Lm. And here I've just kind of incorporated the harmonics themselves into this H alpha beta Lm. Yeah.
So I didn't quite understand why we are using the regular H alpha beta regular inside the particle voltage, because that contains H puncture, and H puncture in leading order is H singular, right? So and R is the distance from the particle wire line.
Yeah.
And there's this at R equals to 0, it's singular. So
yeah. Well, this is singular too. This is singular, this is singular, this is not singular. We want to solve for a non-singular field, H residual.
okay, so that cancels H's, is it?
So this is HS plus HR. So the S part cancels the puncture. So this is always nice and regular. So as indicated here, this is a regular field plus something else that's also regular. So yeah, we've canceled all the singularities by moving the puncture to the right-hand side. We've not introduced them. Yeah. Okay, yeah, so here, when I write H alpha beta Lm, I'm including the harmonics inside that object. So then we just have a sum over Lm. And then the magic is, because this is uniformly convergent, I can actually just bring this limit inside. Then I just have the modes at the particle, modes of the retarded field at the particle, minus the modes of the singular field at the particle. And I just add up those modes, and that gets me my regular field at the particle. So this is called mode-sum regularization. Here I'm doing it just for the regular field itself. I can take a derivative of that, and then I've got the same formula for the force. And anything constructed from the regular field, I can do that same way. Okay, so in the rest of the lecture, I'm going to change topics, treating this as complete. This is the full self-force formalism, kind of in a generic framework. I'll make it much more specific probably tomorrow. So now I want to switch over to describing orbital motion, which is another big piece of the puzzle. So far, everything I've said is true actually just in a generic space-time, not specialized to binary. Now, to understand how things happen in a binary, I want to first look at just orbital motion. So any questions about this before I move on? Yeah. Yep. The residual field, yeah, yeah. Yep. Yep. This is our junction condition at the boundary. But the puncture we know analytically. The puncture is known analytically, that's how we're able to actually calculate the source. So we already know the puncture. So the matched asymptotic expansions calculation already gives us the puncture. We've already got that. Then we're numerically solving for the residual field outside, retarded field inside. Sorry, other way around. Residual field inside, retarded field outside, and imposing this junction condition. Now it's not like we're solving for the residual field here on its own, and then separately solving for the retarded field out here on its own. No, we're solving it all together, all at once, subject to this jump condition. Yeah. Okay. So yeah, the things to keep in mind are, after all the hard work, what we end up with is these coupled equations. This one, and the equation for the trajectory. Together with this practical way of implementing those equations, or solving those equations. Okay, so now I want to switch to orbital motion. So this is going to get much simpler. But with prettier pictures. Okay, so orbital motion. So we want to solve that equation. We want to solve d squared z alpha d tau squared equal to some small force, some small force per unit mass. This is what we want to solve, but in order to solve it in an effective way, I'm going to say first, let's look at geodesics. And from the structure of this, like I described in the very first lecture, from the structure of this, we're going to learn how to deal with this. So I'm looking at geodesics in the Kerr background, the external background. So Kerr has two killing vectors and one killing tensor. And each of these is going to give us a conserved quantity for a geodesic. So the killing vectors I'll write as T alpha, which is just 1 in the t direction, 0 in every other direction, and phi alpha, which is just 1 in the phi direction, and 0 in every other direction. Here I'm assuming I'm working in Boyer-Lindquist coordinates, tr theta phi. And r is now the Boyer-Lindquist radial coordinate in the big external background spacetime, it's no longer distance from the particle. And the killing tensor is k alpha beta equal to 2 times a quantity called sigma that pops up all the time, L alpha n beta. So these are the same L and N I mentioned in the context of the Tucholsky equation. This is the radially outgoing null vector and the radially ingoing null vector. Plus r squared g alpha beta. Sigma is r squared plus a squared cos squared theta. Okay, so we've got 3 killing quantities. Now, from each one, we're going to get a conserved quantity for a geodesic. It's then going to allow us to easily solve the geodesic equation. So we have constants of motion. The energy, which is minus u alpha t alpha, or simply minus ut with index down. We have the angular momentum around the spin axis of the big black hole. This is u alpha phi alpha, or simply u phi with index down. And we have something called the Carter constant that I introduced back in the first lecture, which is the killing tensor contracted with u. How many of you have not seen killing tensors? Quite a few people, okay. Okay, so killing tensors are a bit more obscure than killing vectors, but anytime you have a killing tensor, which satisfies this equation. So this is basically just a generalization of the killing vector equation. For killing vector, you just wouldn't have this last index. You just have one index instead. So this implies that C is equal to a constant. And the derivation of it being constant is basically the same as derivation that E and L are constant. You just take a covariant derivative along the world line. So dc d tau is u mu grad mu k alpha beta u alpha u beta. If this acts on that, then we can apply this equation to get 0. But if this derivative acts on u, well, then we can apply the geodesic equation to also get 0. So this just gives us 0. Okay, so we have 3 constants of motion. Now, very often, rather than using C, we use something that's also called the Carter constant. Q and C are both called the Carter constant. And Q is just a linear combination of the other 2, or the other 3, sorry. Actually, it's not a linear combination, but it's a combination. A, B squared. So the reason Q is often used instead of C is that if the spin goes to 0, then Q reduces to Lx squared plus Ly squared. So the other 2 pieces of the momentum. And because of that, if you have a motion confined to an equatorial plane in Kerr, that corresponds to Q being 0. So if Q is 0, the motion is confined to the equatorial plane. If Q is non-zero, that tells you how much it's inclined away from the plane, how much it's oscillating around the plane. Okay, now we're going to use these constants to get expressions for the velocity. So let's just expand that out. We've got E is minus G T T T dot minus G T phi phi dot, where here a dot indicates d by d tau. It's a proper time derivative. And Lz is G phi T T dot plus G phi 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 dot. And let's write down C rather than K, or sorry, rather than Q. And C is, something times T dot squared plus something times T dot phi dot plus etc. So all of these are just combinations of the velocities, or the components of the velocity. And then we can just rearrange those equations together with one other equation, which is just the normalization condition that G alpha beta, U alpha, U beta is equal to -1, just by definition of the proper time. So this gives us a fourth equation. So we then have 4 equations for the 4 quantities T dot, phi dot, R dot, theta dot. So we just rearrange those equations to get expressions for each of those dotted quantities. So we get that quantity sigma times T dot. I'm not going to write these down because they're pretty long. Well, they're simple in Schwarzschild, but pretty long in Kerr. We have some function of r and theta on the right-hand side. Sigma r dot squared is a function just of r. Sigma theta dot squared is a function just of theta. And then sigma phi dot is a function of r and theta. So you never have any dependence explicitly on t and phi because the space-time is stationary and axisymmetric. So everything on the right-hand side can only depend on r and theta, but then in these two cases, you get only r and only theta. But remember that sigma depends on both r and theta. It was r squared plus a squared cos squared theta. So to get rid of that sigma, we introduce what is called Meno time. Meno time, lambda. And that's defined by the condition that d tau d lambda is that sigma. So that means over here, I have d tau d lambda times dt d tau. So the d taus just cancel, and I get equations for dt d lambda equal to v t r theta, dr d lambda squared is vr of r alone, d theta d lambda squared is v theta, it only depends on theta, and d phi d lambda is v phi of r and theta. So in this form, we now have decoupled equations for r and theta. So we can solve this for r as a function of lambda. We can solve this for theta as a function of lambda. Then once those are known, then we can solve for t as a function of lambda and phi as a function of lambda. So this decoupling was first found by Carter back in the 70s, but this very simple way of formulating it is due to this guy Meno, who used to be in Cellforce. Yeah. That's an excellent question that I don't know the answer to. Yeah, that's a very good question. Okay, that sounds like it's probably the same, yeah. Yeah. No, no, you don't have a lens vector. No, yeah, that's definitely true. No, no, yes. So here I'm using the existence of Carter to prove separability. But it's if and only. Yeah. Okay. Yeah, okay, so still got 15 minutes. So we can take these as our equations to solve. And the one important thing about them is that the structure of these terms on the right-hand side, these functions on the right-hand side, v of r and v theta of theta, they actually determine basically what kind of motion you're going to get. Because anytime this function is 0, that represents a turning point where dr d lambda is 0. And similarly, anytime v theta is 0, that's a turning point of the polar motion. So it's like reaching a maximum or a minimum inclination. And then the number of roots of the right-hand side tell you if you have multiple turning points. And so that is exactly what we get. We get 2 turning points for each one, plus actually some additional roots that are unphysical, that are outside where you would be solving the equations. So we get 2 turning points for r and theta, which means that for bound motion, you're just oscillating between those 2 points in r and in theta. So I'm going to use that to introduce a quasi-Keplerian parameterization of the geodesic motion. So I'm going to write R as if it were an ellipse. So if this psi were actually phi, this would just be an ellipse in the physical spacetime. This is not equal to phi, and that's indicating that you have precession of perihelion. And then similarly, I'm going to write, rather than writing an equation for theta, I'm going to write an equation for cos theta. And this is similarly just going to be oscillating between minimum and maximum. So let me take the maximum of cos theta and multiply it by cosine of psi theta. So when psi theta is 0, we are at the maximum of cos theta. Now I can also write this more intuitively in terms of an inclination angle as sine I, where I is the inclination angle. So cos theta max is just the maximum inclination, or if you multiply by r, it would be the maximum inclination. This is the inclination angle. So I here, this distance here is r sine I, and that's also equal to r times, this distance is theta, or the angle is theta, equal to r times cos theta max. I guess this is actually theta min. Cos of theta min gives you cos theta max. Okay, so this is trying to make things as much like a Keplerian orbit as possible, but this is in terms of phases, psi r and psi theta, that are not, phi or anything like that. They're not phi, they're not theta. So this is the axis of rotation, say z hat. Yeah. So theta equals pi over 2 is the equatorial plane that's orthogonal to the spin axis. Yeah, so inclination here is the inclination off of the equatorial plane. Okay, so if I just take this as my ansatz and I throw it into all my equations over there, what I get is some non-trivial equations for d psi r d lambda and d psi theta d lambda. I'm going to impose that dp d lambda is 0, I'm missing an e here. E. dE d lambda equal to 0, and di d lambda equal to 0. Just like you would have for a Keplerian orbit. These are constant quantities. So we have the semilattice rectum P, the eccentricity E, and the maximum inclination angle I as constants. Then when we plug that in over there, we get equations that I'm not going to write down. D psi r d lambda is, let me write it as some kind of script f. It's a function of psi r and of p, e, and not inclination, I think, but I could be wrong. Let me leave inclination in there just in case. No, it can't involve inclination. And similarly, d psi theta d lambda is some function of psi theta, p, e, and I. I think I'm right that I doesn't appear here. But... Okay, so here everything is 2 pi periodic in these phases, psi r and psi theta. If I change either of them by 2 pi, the r motion comes back to itself, or the theta motion comes back to itself. Now, in practice, when we go to solve the Einstein equations, we don't really care about this parameter lambda. What we care about is the time of an asymptotic observer, or Lindquist time t. So we care about that because it's a time that's naturally adapted to the stationarity of the background spacetime. Then also it gives us the time at the detector. So it's useful to rewrite things in terms of t rather than lambda. And if we do that, let me write them as just a single equation. D psi alpha dt is some function I'll call omega alpha. That's a function of the psi betas. And let me also introduce, let me introduce 2 things. I introduce psi alpha, that is psi r, psi theta, and just phi itself. And I'm going to combine all of my other parameters into something called pi alpha, which is p, e, and the maximum inclination angle. So in terms of those, we have these rates of change of the phases. These now depend on both psi r and psi theta, whereas back over here, d psi r, d lambda only depended on psi r, and d psi theta, d lambda only depended on psi theta. So when I switch to coordinate time t, I kind of reintroduce the coupling. But I want to do that because I want to define frequencies frequencies of motion. So I've written this as an omega as if it's a frequency, but if you have something oscillatory, that's not a good measure of frequency. So the frequencies are basically the averages of those. Where I'm averaging over some definition of angles or some definition of a long time scale. So I can point you to where this is defined carefully. But the point is, the average frequency is giving us really the physical period of motion. And these are what actually appears directly in the waveform, these frequencies. Then there was a question about resonances the other day. Generically, these three frequencies are incommensurate. So let me write that. Generically, n r omega r plus n theta omega theta plus n phi omega phi is never equal to 0 if nr, n theta, and n phi are integers. So this is generically true. And then we say these frequencies are incommensurate. Now the phi frequency isn't so important for the intrinsic dynamics because the intrinsic dynamics doesn't depend on phi. Phi factors out due to the axisymmetry. But if you ignore the phi here, just take n phi to be 0, you do have very important things happening when the sum of these two gives us 0. So when nr omega r plus n theta omega theta equals 0, this is a resonance. So we get an orbital resonance. So these are very special orbits. If we kind of draw the motion in the r theta plane, so r theta, if you have incommensurate frequencies, this will just keep moving around and never come back to itself. The trajectory will never return to itself. But if you have a resonance, then it comes back to itself. So you can have 2-to-1 resonances, you can have 3-to-2, you can have all these lists of different resonances of how many periods of radial motion relative to how many periods of theta motion brings this curve back to itself. This looks like a 2-to-1 resonance. Now here this is for geodesics. So if you have a geodesic on a resonance, it just stays on a resonance forever. In an actual binary inspiral, frequencies keep evolving. So you don't have this holding true forever. And so you actually evolve through the resonance, but you get kind of some rapid changes as you cross the resonance. I think I should have time to discuss that a little bit more tomorrow. Okay, one last thing today, and I guess I won't have time to show you some pictures. One last thing today. On the first lecture, I introduced some phases that had constant frequencies, angles. I'm now going to tell you one way to get to those. So right now we have d psi alpha dt is omega alpha, which is not a constant. It's evolving with the phases. And we have d pi alpha dt equal to 0. I want to transform to new variables where I get a constant frequency. So let's define phi alpha, curly phi alpha, to satisfy such that d curly phi alpha dt is equal to those constant frequencies, which are just functions of the p, e, and inclination, maximum inclination angle. So I want to find a transformation that brings me from psi to curly phi. The transformation I can write as psi alpha is phi alpha plus an oscillatory piece, such that the curly phi is basically an averaged version of psi. So I'll write that oscillatory piece as delta psi alpha phi beta. This will only depend actually on phi r and phi theta. And the constants of motion. And this I want to be perfectly periodic theta, so that if I kind of average away oscillations, the average of psi gives me phi, curly phi. So to find out what this function is, or basically just to prove it exists, but in practice you do need to know what it is, we just substitute this expression for psi into this equation here. So we get on the left-hand side omega alpha, and on the right-hand side d phi alpha dt plus, so all these pi, the p and e, etc., are constants. So when a time derivative acts on this, it's only acting on the phase dependence, the curly phi's. So we get d phi beta dt times derivative with respect to the phi's, delta psi. Now I want to impose that this is true. This is defining for me what I want my coordinates to do. And so then this becomes omega alpha plus omega beta d curly phi beta delta psi alpha. So let me just rearrange that for the unknown function delta psi. So we get omega beta d curly phi beta delta psi alpha equal to lowercase omega alpha minus uppercase omega alpha. So basically what's happening here is I have an oscillatory function lowercase omega. When I subtract uppercase omega, I'm removing the average of lowercase omega. So this is now a purely oscillatory function on the right-hand side and a purely oscillatory function on the left-hand side. And then I can just solve that equation. So this is called an averaging transformation. So this is just a coordinate transformation of my parameters. So then I have the equations I want to end up with, the kind that I introduced in the first lecture. I've got d phi alpha dt is omega alpha, and I got d pi alpha dt is 0. So I've reduced the geodesic equation to these equations. Okay, so I'll end there, but might have time for questions, if there are any. Nope, this is an exact coordinate transformation. We don't lose anything. Okay, let's end it there then.